All right, I thought we'd look at another example of the second derivative test to discuss the concavity of a given function and then find any places where the concavity switches from concave up to concave down and vice versa. These are called the points of inflection. Our given function is x cubed minus 6x squared plus 12x. We are to determine the concavity, find any intervals where the function is either concave up or concave down, and then use that information to find any points of inflection for the function. Concavity is determined by the second derivative. Let's see where the second derivative changes sign. That will be where the second derivative is equal to 0. In other words, the critical numbers of the second derivative. I'll first find the first derivative. So f prime of x equals 3x squared minus 12x plus 12. Since we're doing the second derivative test for concavity and points of inflection, I'll need to find the second derivative. So 6x minus 12. Let's see where 6x minus 12 is equal to 0. In other words, the critical numbers of the second derivative, where the second derivative switches sign from positive to negative or negative to positive. Add 12 to each side, divide by 6, and I get 2. I know that the second derivative switches sign at 2 from either positive to negative or negative to positive because this is where the second derivative is equal to 0. Let's investigate the sign of the second derivative of this function by making a number line. Or f double prime of x. I know that this function, the second derivative, only switches sign at 2. So therefore, everything before 2, from negative infinity to 2, it has to be one sign. It can't switch anywhere else. And then from 2 to positive infinity, it has to also be only one sign because it can't switch anywhere else. Pick a number that would be, for example, less than 2 and substitute it into the second derivative, about 0. What is f double prime of 0? 6 times 0 minus 12. That would be a negative number. So I know that the second derivative is negative for any value less than 2. Pick a number greater than 2, for example, 3. Let's see what f double prime of 3 is. I want to determine if it's a positive or negative number. 6 times 3 minus 12 is positive. So I know that the second derivative for this function is positive between 2 and infinity. In other words, we are concave down, or this function is concave down. From negative infinity to 2. Not better infinity than that. There we go. I know it's concave up from 2 to positive infinity because the second derivative is positive on that interval. Where does the second derivative switch signs? That's where we'll have a point of inflection. Well, the second derivative switches signs at 2, from concave down to concave up, from a negative second derivative to a positive second derivative. We have a point of inflection at that coordinate, at x equals 2. Let's plug 2 into the original function to complete this ordered pair, to find the rest of this ordered pair for our point of inflection. F of x is x cubed minus 6x squared plus 12x. We're going to plug 2 into that function. 2 to the third is 8. 6 times 2 squared, that's 6 times 4. 12 times 2 is 24. 24s cancel out. I have 2 comma 8. the intervals where our function is concave up or concave down, and the point of inflection for the function. Now, since we're talking about a graph of a function, it's always a good idea to look at the graph on some graphing utility and confirm our answer. All right, so I've got x cubed minus 6x squared plus 12x. There's the graph of our function. I can make it a little bit better window by using my wrench icon to adjust the settings. Let's maybe go from -5 to 5. The x-axis. And maybe -15 to 15 y. Now there's a decent picture of my function. I know that it has a point of inflection at 2, 8. I'll graph that right there. You can see from -infinity to -2, that would be this left-handed portion of the function. It's opening down, it's concave down. From thereafter, from 2 to positive infinity, on the right-handed portion of the graph, it's concave up, looking like a bowl or a cup, concave up. So I believe this matches with the work that we had on the board as we were applying the second derivative test.